Hello everyone, my name is Shlok and we are LoopMIT, the official Hyperloop team of Manipal Institute of Technology. Next slide please. So our team was founded in the year of 2019 and since then we are a group of 25 highly motivated and dedicated students who are trying to build our first Hyperloop prototype pod. So now today we are going to present our pod overview, followed by the mechanical subsystem and a propulsion subsystem. So Saugata is going to carry forward the pod overview.
Okay, everyone. This is the mechanical subsystem of LoopMIT, which consists of components like aeroshell, chassis, braking system, and the guidance system, which consists of lateral control module and vertical stability system. We'll be discussing more in details later in the presentation. This is what the propulsion system of LoopMIT looks like. The further details will be explained by my colleague in the later slides. I'll hand over to Sahil.
So I'll start again. I'm Sahil Sinha, the Electronic Control System Head of LoopMIT Manipal. I'll be presenting to you the electronic systems. The very first thing that we have is the battery management system. We are planning to go with lithium polymer batteries. We have tested with other batteries as well, like lithium polymer phosphate. But under the given circumstances that we have and looking at the scenarios that we want to build the pod in, I think the best will be lithium polymer batteries, the advantages of which you can see on the screen. Moving along, the ratings of the battery management system that we have designed and planned is on your screen. Along with this, to manage the battery management battery pack, we are planning to go with ESP32 as the microcontroller, and it will be rated at 250 volts, and the current density would be 12 ampere hours. So talking about one of the most important part of the electronic component, that is the sensors. So in under this component, we will be sensing the ins and outs of the pods and whatever things that are required by us along with the other subsystem groups, like in order to apply the emergency brakes by the mechanical subsystems for if there is a high rise in temperature, or for the levitation and propulsion to figure out how much distance is there with a gap height sensor. So along with those things, we would be able to manage. And for managing the sensors on the pod, we are planning on using ESP32 and STM32 as a microcontroller. We are also planning on implementing 2 to 4 layer of PCB design, which will help us to enable a easier circuit and in a most efficient way. So this is the future aspect that we are currently planning on building, which the user interface, a user-friendly graphical user interface through which we can overview and control the pod, and all the aspects of the design and the sensors that we saw in the previous slide would be visible at the go, and any emergency stop or stop and go motion would be from the outside control or the inside control as per required. So the mechanical system would be handled by my.
Hello everyone. The aeroshell is a critical component of the pod since it protects all the pod's components while the aeroshell is a critical component of the pod since it protects all the pod components while also assisting the propulsion system in moving the pod more efficiently by causing less drag. We are manufacturing the aeroshell using bidirectional carbon fiber. The estimated weight of the aeroshell is around 8 kg. The aeroshell has been built in such a manner that it will feel as if it is traveling in a vacuum when it is not. We had several prototypes of the aeroshell, but we picked this one to make the pod appear more streamlined. As you can see, we conducted the simulation testing and had a positive result providing our design concept. As per simulations, we have achieved a maximum speed of the pod of about 34.2 meter per second, and the pressure distribution all over the body has been shown. The further components of the mechanical subsystem will be handed over by Himanandan.
As you can see, our chassis is an inverted U structure. Initially, we designed a monocoque, but it was not structurally compact enough at high speeds, and it was hard to mount all the different parts without affecting the stress limit of the chassis. We are using aluminum honeycomb as the core for the chassis and CFRP on both sides. Coming to our braking system, we have decided to go with friction brakes. It's going to be mounted at the back end of the pod, so the center of mass of the pod will remain at the center of the whole pod. And to make sure that the pitch is very less during the deceleration, Regardless, the materials used, we chose Kevlar pads for the braking pads, so that the coefficient of the friction is such that the damage to the I-beam will be very less. And regarding all the mounts, we chose aluminum for the mounts. We are also going to manufacture all the components in-house, as most of the components we need are not available on the market. Regarding the working, as you can see, as soon as the double acting cylinder is actuated, the brake pads are going to clamp to the I-beam. For we are using the same, but with a different mechanism. So in case there is a power loss or the pressure loss in the air tank, the brakes are going to be automatically actuated. Coming to our guideway systems, this is our lateral control module. Two of these are going to be mounted at the back and front end of the pod. We are using polyurethane wheels with aluminum core for the wheels. All the mounts and links are going to be made in-house with aluminum using CNC machine. Coming to the working, it consists of a wheel attached to a link that is attached to an extension spring. The extension spring transfers the force into the extruded plate placed on chassis. The spring is designed in such a way that the wheel is constantly in contact with the track. Like LCM, two of these are going to be mounted at the front and back end of the pod, similar with the similar wheels. That is in materials, but with different dimensions. Our reasoning for using wheels was primarily to improve roll stability. The lack of a stub track meant that we had to either make the pod extremely well balanced, or else have a reasonably stable roll axis. Coming to the working, it consists of a classic spring damper system that acts as a main vibration and bump mitigation mechanism, where the spring handles the force handles that we're going to explain. As the name suggests, the
Rahul,
this subsystem
can
deal
you
with
stop for
propulsion
a
of the
moment?
pod.
Yeah, so the entirety of Himanandan's last part was blotted out because I think connectivity issues. Yeah, sorry about that. So could Himanandan repeat the last part?
Yeah, sure. The vertical stability system.
Yeah.
Okay, similar to LCM, we are using VSS to maintain the roll stability. Our reasoning for wheels was primarily to increase roll stability because the lack of a stub track meant that either the pod has to be extremely well balanced, have a reasonably stable roll axis, or have wide contact path. Coming to the working, it consists of a classic spring damper system that acts as the main vibration and bump mitigation mechanism, where the spring handles the force applied and the damper handles at which the speed of the shock absorber compresses and decompresses. Yeah. Over to Rahul. So he'll continue explaining the propulsion subsystem. As the name suggests, this subsystem deals with the propulsion of the pod. For the propulsion of our pod, we are using a single-sided linear induction motor. The linear induction motor is supplied with three-phase current, which will generate a traveling magnetic field and propel the pod. This version of our LIM has 6 slots and 2 poles. We chose to go for carbon steel as the material for our pod's core, as it was readily available and suitable to test our lamination process. In this video taken of a test LIM, you all can see that the aluminum sheet is propelled in the right direction when three-phase current is supplied by auto transformer. In the second version of our LIM, we decided to increase the number of slots in order to facilitate for the weight of our pod. We also changed the material from carbon steel to electrical steel in order to attain higher permeability and lower corrosivity. From one of the simulation videos of our version 2 LIM, we can see the generated flux at any point on the LIM along with magnetic field density. We have used 150 turns and 16 gauge copper wire for this version of our LIM. These are our sponsors.
Next slide, please.
Thank
Yeah, we'd
you.
like to thank you all for bearing with us and sorry about the technical glitches once again. And we're open to any and all questions.
Hello everyone, am I audible to you all?
Yeah, go ahead.
Audible. Go on.
Yeah, as per your design in your frame, you had mentioned two section for braking caliper. Can you explain why you're going for two braking caliper if you're using for single sided linear action motor?
Sorry, can you repeat your question?
As your frame, as we can see in your frame, there is a two section given for your applying brake, and if you are applying two sides of brake, and if you are going for single side linear induction motor, so why you had opted for double sided braking system instead of going for one if it doesn't produce much speed with a
Braking
single side?
system, is it? Are you talking
Yeah,
about the braking system?
braking systems. Yeah.
What is the exact question regarding the braking system? Why are we going with?
Can you just go with that frame where you had mentioned about the braking systems?
Yeah.
Yeah, here you can, not here. That frame, the carbon fiber frame you had shown
Yeah.
to us, where the braking calipers were applying. So yeah, it is that replica of that. But you can understand from my question that you had groove two holes, that is the square holes on to your frame for applying braking. Why you had applying two sides of linear braking system instead of going for single braking system if it doesn't produces much speed as you are opting for?
Oh, so the forces along the y direction will be equal, like total net force will be zero along the y-axis. We need only friction to act, right? Otherwise, there will be a pitch cause. So we have to apply forces above and below the item. We apply only at the top.
The question is as simple as why you are opting for double-sided braking system at the front of the pod and also at the back of the pod.
No, only one at the back. Okay, I think you misheard me. I said only one at the pod. Only one at the
Okay.
back end of the
Can
pod.
you go back to the
Yeah.
presentation? Just slide back. Then, yeah. This is the only that picture I was curious about. You had mentioned two grooves here. So, what is the reason behind that?
Oh yeah, that for only for brakes, the first one. The second one, yeah, it was. I think it's a mistake we did. It will only be one at the back. Yeah, our mistake. Sorry.
So, it will be back only. I mean,
Yeah,
it will
it
be
will be only
only
one
one
at the
groove
back.
for
Yeah,
braking
only one
system.
at the back end.
Okay, that was
Yeah.
that actually make me curious about if you are using two-sided braking system instead of going for one.
Yeah, no,
Okay,
because
no problem.
our pod is one system is enough for our pod.
Yeah. Yeah, got it. Thank you.
All right, guys, and then we've reached the end of it. Huge thanks to all the teams, especially I know there were some technical difficulties, but thank you for persevering through it.